sorry. 4.1 is preliminary theory. Okay, and for a lot of it, we're going to look at, maybe I could divide this into 4.1.1, 4.1.2.3. Okay, so within 4.1, there's 3 sections, let's say. Okay, the first focuses on IVPs, and for this unit, we're studying IVPs that have coefficients in terms of x times the nth derivative, and so on and so forth. These equations were called what? Nth order, but what kind? Linear, good. So all the powers are to 1 for the derivative, so we know it's a linear equation. We've studied pretty much this portion the last unit, right? First order, and then if we went second order, we had substituted. Oh yeah, oh my gosh, I forgot about Eric. Welcome to class, Eric. You didn't miss much.
Yeah, I know. I saw the 4 or something.
Sorry about that. At least it wasn't like that one time. I left a student out there all period, and then 20 minutes later I remembered that he was out there. And I went to go get him, and he was asleep on his backpack in the hallway. I felt really bad. It was okay. Anyway, moving on. So we've studied these first order linears, right? These last 2 terms equal to gx. If we had anything that was not first order, we usually worked our way around it by doing a substitution. Now we're going to actually go ahead and study second order, third order, basically anything higher than a first order, and we'll go through that. So we have linear equations and subject to some initial conditions. Y of x naught equals y naught. Y prime of x naught, let's say, equals y1. Y double prime of x naught equals y2, and so on, down to the n minus first derivative. The important thing here to note is that there's n conditions. Okay, so for first order we had 1 initial condition. If we have an nth order, we will have n conditions, and they just go up in the order of the derivative each time. Okay. Now what we're going to look for is the solution that contains x naught satisfying these conditions on, I don't know, some interval I. Okay, now we'll talk about these briefly too. If the conditions look a little different, so if the conditions, instead of the ones that we listed up here, look something like this, y of x naught equals y naught, y of x1 equals y1, and so on. down to y of x sub n minus 1 equals y sub n minus 1. Okay, then this is like an initial value problem. We still want these things to satisfy all these conditions, but we call this a boundary value problem. Okay. I still feel really bad, Eric. I'm sorry. If it makes you feel better, I locked myself out of my house today. As I left, I realized I left my keys in this little record bowl that we have. It's like a warped record made into a bowl. Everything's in there. Keys. Fortunately, I have my wallet, but yeah, not a good start to today. That's all right. Okay. Questions so far? Hopefully not. All right. Just like we did last unit, we're going to talk about existence of unique solutions. Okay, and there are several conditions that need to be met. Looks something like this. Okay, so we're going to let the coefficients back up here. These are the coefficients, a sub n of x, a sub n1 of x, and so on. We're going to let all those coefficients and whatever function the equation is equal to, which is g of x, be continuous on an interval I with the leading coefficient, a sub n of x, never equal to 0 for all x in this interval. If we have an initial value in the interval then a solution to the IVP, I'll just say above. So we're talking about the IVP that we listed right at the beginning, will exist. So it exists and is unique on that interval. Okay, so in order for a solution to exist and be unique, sorry, not for it to exist, but in order for a solution to be unique, all the coefficients have to be continuous functions on that interval that we're interested in, and the leading coefficient can never be 0 for any value in that interval. Okay? And if that's the case, assuming that the initial conditions that were given are also in that interval, then we say that we know that there is a unique solution. Okay? So that's pretty much what we're looking for. So, for example, let's say we have y equals 3e to the 2x plus e to the minus 2x minus 3x. And let's say that this is a solution to the IVP y double prime minus 4y equal to 12x. And the conditions were y of 0 equals 4 and y prime of 0 equals 1. Okay, in a couple of days, you'll actually be able to, well, not a couple of days, more like about a week or so, we'll actually be able to solve this differential equation and say, here's a solution, without too much hesitation. But for now, you're just going to have to trust that this is a solution, and now the question is whether or not this is unique. Okay? Well, what can we say? What are the coefficients for the differential equation here? Since 1, negative 4, and 12x are all continuous, on what interval? Everywhere, right? And what's the leading coefficient? Since 1 never equals 0 on that same interval, y is unique. Okay, so that's the main idea there. Eventually we'll find the solutions and we'll know they're unique. Right now, you just kind of want to know, based on these conditions and the differential equation at hand, will there be a unique solution for it? Okay, and in this case there is. Okay, let's look at another one real quick. Okay, so let's say this differential equation, x squared y double prime minus 2xy prime plus 2y equals 6, has solution, what is it? Y equals cx squared plus x plus 3. What can we say here? I mean, we didn't get any initial conditions, so let's just be as general as we can. What are the coefficients that we're looking at? Okay, so x squared, negative 2x, 2, 6. Where's the problem? I mean, they're all continuous, but the issue is, yeah, x squared equals 0 when what? X is 0. Okay, so this violates the existence theorem. So y is not unique. Well, maybe we should say it's not guaranteed to be unique, but so if we have an IVP and maybe we're looking at a different interval, not including 0, then we're okay, but since we don't know where we are, this is what we can say. Okay? It could be. Yeah, these are not if and only ifs, it's just one way. Like if these conditions are met, it's a guarantee. If they're not met, we don't know. Okay, so this kind of explains the background for IVPs, existence of unique solutions for IVPs. Let's look at those BVPs real quick. So what does this even look like? Well, this scenario is actually much easier to draw than having, 5 or 6 initial conditions with all the derivatives being satisfied. This just means that x naught, y naught, x1, y1, and so on, down to x sub n minus 1, y sub n minus 1, that all these points must be what? So okay, let's go back here. Let's say I have a family of curves that satisfy, the differential equation. How do I know which one is the solution to a boundary value problem? Well, for an IVP, what did it have to do? It has to go through that point, right? X naught, y naught. For a boundary value problem, it has to go through all of these points. Okay, so maybe this is the solution, and the reason it is because we know that it hits x naught, y naught, x1, y1, and so on. Okay, so then we can say that this curve this satisfies the BVP since it goes through the required points. Okay, so that's what it looks like geometrically. Let's look at an example in context. Right, so let's consider the boundary value problem. Y double prime plus 16y equal to 0 with y of 0 equal to 0 and let's say y of pi over 2 equal to 0. And the solution, which is y equal to c1 cosine 4x plus c2 sine 4x. Okay. Let's actually go ahead and try to find these constants. So how do I find C1? Well, plug in the points. The condition was that the solution should be 0 when you plug in 0 for x, right? So plug in 0 into cosine of 4x. The cosine of 0 is just 1. So we get C1 plus, and then we have C2, sine of 0 is 0. So here we get that C1 has to be 0. Okay? So now if we try to find C2, we would try to plug in pi over 2. And that has to equal 0. And if I plug pi over 2 into the inputs, we get cosine of two pi and then we also get cosine of 2 pi is 1. If I plug in pi over 2 in here, sine of 2 pi is 0. So again, we confirm that C1 is 0. So what does this mean? Yes. It means that C2 is completely arbitrary. So the only thing that we need to have is that C1 has to be 0 in this case, but C2 can really be anything. Okay, so here's why. So if I graph, if C1 is 0, then basically what we're talking about is a function that looks like sine of 4x. So the period would be 2 pi over 4 or pi over 2. And then here are the points that we're talking about. Here is 0, 0. Here is pi over 2, 0. So these were the boundary conditions. And now obviously, what is the C2 effect for the sine graph? Amplitude. So we can vary that, and we're still going to meet those conditions. So we have several options here. So in this case, we say that there are infinitely many solutions in this case. The reason I'm pointing this example out, okay, so in this case we have infinitely many solutions, but if we go back to the differential equation, y double prime plus 16y equals 0, according to the existence theorem, okay, we have a coefficient of 1, coefficient of 16, coefficient of 0. Those are all continuous, not a big issue. 1 is never equal to 0, okay? If this were an IVP, this would be no problem. Does that make sense? But the point here that I'm making is that when the conditions are met for a boundary value problem, I'm sorry, when the conditions are met for existence, there could be several solutions, a unique solution, or none. And this is for boundary value problems. Okay, so you need to be careful with the context of the problem. If it's an IVP and the existence conditions are met, we're good to go. If you know it's a boundary value problem, then we really don't know anything, even if those conditions are met. Okay, so for an IVP, if we go back, let's kind of look at these side by side. So here's the difference. Boundary value problem, look at it's all about the conditions that are given to you. They're all different points along the solution curve. See what I'm saying? You plug in 0 into the solution, you get 0. You plug in pi over 2 into the solution, you should get 0. For an IVP, the conditions are not all about the solution curve. It's one is for the solution curve, then what's the next condition? For the derivative, and then if we had a higher order, we'd have every derivative after that. Well, for the case that we did with the boundary value problem, yes. But like in this case, you will have a unique solution. Okay, and all you would do is plug in 0 into y, figure out a constant, whichever one it lends itself to, and then you'd plug in the condition 0 into the derivative. So you'd have to, like if we actually wanted to solve this, well, it's already solved for. Here's your C1, your C2, you know what I mean? But if this was written in format where we had a C1 and a C2, you can go back in here and plug them in, and this is what we would have gotten for those constants, 3 and 1. Does that make sense? Yep.
Do the points for like y0 and y prime 0, do they always have
Yes. Yes, that's the other point to make. Always going to be at the same value for the IVP. You're not going to have, yeah. Yep. So it's either going to be y of 0, y prime of 0, y double prime of the same point. Boundary, I mean, that's the other thing you can look out for, too. If you see these x values changing, okay, it's probably a boundary value problem. Okay? Anything else? All right. Then let's at least talk about the idea in the second part of 4.1. Which is linear dependence and linear independence. Have you guys seen those videos of professors going nuts when the cell phone goes off in class? Sometimes I think about that and how I would lose my job here because I can't do that. Okay, thank you. Not that I've ever do that. Although I have been known to answer phone calls in the middle of class. That always goes over well. What's that? Yeah, like if a student's cell phone starts ringing in class, I've answered for him. One time it was a parent, and they asked for the student, and I was like, this is her teacher. How can I help you? Oh, is she? I'm like, she's learning right now. Can she call you back? And she felt embarrassed, of course. And the other time it was like a college admissions person trying to call, and I was like, oh, that's kind of important. Why don't you go? Yeah. So I let her go take care of that. But yeah, I don't break things. Okay. Here's the definition. A set of functions, and this is very important. Well, this whole section is very important, but a set of functions f1, f2, and so on is linearly dependent on an interval I if there exist constants C1, C2, C sub n not all equal to 0 such that C1 f1 of x plus C2 f2 of x and so on equals 0 for every x in the interval. So if we have a set of functions at hand, which right now to you probably doesn't make much sense, but eventually when we start solving these differential equations, we're going to find some functions, and we're going to be interested in whether or not these functions are dependent versus independent, and that'll help us determine whether the solution is a unique one or not. If you can arrange the functions so that you can find constants so that they basically cancel out and equal 0, then you can think about them depending on each other, and that's what we mean by dependent. Okay, and then obviously the definition for independent pretty much the opposite. Well, it's the exact opposite. We say that a set of functions f1, f2, and so on is linearly independent on I if the conditions are not met for being linearly dependent. Nothing too fancy there. Okay, and real quick, actually no, let's not do that. It's a good place to stop. All right, so we'll pick up with this tomorrow. I'm about 10 minutes behind where I wanted to be. That's okay. We'll try to pick up the pace. All right, see you guys tomorrow.